For example, if we talk about coil AA dash, we are effectively looking to maintain certain value of current over a given period of time. And assuming that the information about time is available, we have to maintain certain value of current over this duration. So one of the option could be that we can have asymmetrical structure for the coil, asymmetrical H bridge, and the IGBTs say 1 and 2. These can be turned on to set up the current up to the desired value, and then the options of whether we want to have a freewheeling of the current through one of the diode, or we would like to have a more controlled reduction of the current. So effectively what we are looking for a chopper kind of operation. For maintaining the current at a certain value. So here we can take help of something known as hysteresis control. So we can decide that the current is always going to be confined within a certain band of upper and lower limits. And by turning on the devices, our current can always rise and hit the upper boundary, and whenever it hits the upper boundary, we need to switch off this positive polarity across the coil so that current can fall down. Whether it is falling down through a freewheeling approach or a forced approach, that can be taken as the option for the power converter. So we have basically two options if we talk about the modes of this asymmetrical S bridge. The first mode, in which basically the coil is excited in the positive direction where both the devices are turned on. In this mode, basically the current tends to rise, and because the coil is dominantly an inductance, so we can say that the current is going to be nearly linear with respect to time. Now from here we have two options of controlling this current within the band. We can go for something known as slow decay of current, which means that we are not forcing a quick decay of current from the upper limit to lower limit. We are not forcing a quick decay, but we are providing the current sufficient time so it can decay very slowly, and whenever it comes to the lower boundary, we'll again go back to the mode 1. So in this slow decay process, we are allowing the current to freewheel through the bottom diode. So we have kept the device to turned on, and we have switched off the first device, first IGBT, and the effect is that the current would be freewheeling in that. Now during this time period, this decay is alright. However, if we continue with this mode of decay beyond this time interval, the current may take lot of time to reduce, and this may basically overlap with the negative dou L by dou theta region, and this is where we may generate unnecessary torque in the machine. So we can look for fast decay mode which is more desirable towards the end of the cycle. So basically, because we are trying to have opposite polarity voltage applied across the coil, we can take help of the fact that the current in the coil cannot be reduced suddenly. So which means if we turn off both the devices 1 as well as 2, the current is going to freewheel via the diodes available in the circuit. So as the current takes the path through the diodes, it is going to see a negative polarity applied across that, and this is where we will find current reducing with that rate. This can be utilized for decaying the current in a quick fashion so that we are not violating the time boundary by a good error, so by a high margin. So in this manner, we can find that the current in the coil for each phase can be maintained on an average at the desired value by setting up some higher and lower limits and by following the hysteresis control. So typically the current waveform may look like this. So we are finding fast rise in the current because there is voltage applied across that, and within this time interval there is slow decay option taken because we do not want the current to be switching many times, we do not want the devices to be switching many times, and the slow decay process may help in reducing the switching energy loss. So by following this type of switching or this type of operation, we can achieve a little better efficiency compared to one of the ways of operating the system. So this basically ends the operation of the SRM drive, and we can follow some of the control techniques as well to control the speed and the torque in the SRM based on the required dynamics. Now we'll move towards the next machine, which is another special machine called as the brushless DC machine. So the next machine what we are going to discuss is basically BLDC, brushless DC machine. It's a different configuration where we are having the flipped arrangement compared to the traditional DC motor. So in case of traditional DC motor, we have the stator consisting of the field where through permanent magnet or electromagnet the flux lines are established, and then we have armature which is basically carrying the current for torque generation. Now here the to maintain a uniform direction of torque, the current direction in armature is changed through brush and commutator arrangement. However, when we are flipping this structure, we are taking the permanent magnet on rotor and we are taking the stator or the armature on the stator. It is basically having the arrangement where the brush and commutator assembly is no longer required. However, similar to DC machine, we need to have uniform torque, which means that in case of this other arrangement, we still need to flip the current direction time to time to maintain the uniform torque within the system. So structure wise, BLDC may look like this. Now if we talk about the operation of BLDC, what we are going to have basically is that because of the presence of magnets on the rotor, we are going to have some induced EMF on the stator windings. Now this phenomena is very similar to the permanent magnet synchronous machine. However, the structure of winding on the stator is not uniform as PMSM. It is more like the SRM machine. It is given in a lumped fashion. And which is why the EMF induced by the magnets on the stator coils is basically non-sinusoidal. So this is what makes the BLDC motor different from PMSM machine. Now if we talk about the different coils, as the motor is as the rotor is rotating, it is going to link the flux with different coils, and so different coils are going to see different flux linkage, which will be varying. However, on account of the concentric or on account of the lumped structure, this is going to have a wave shape which may look trapezoidal in nature. So as we can see over here, typical flux linkage for given BLDC where three-phase coil arrangement is there. So what we can find that the flux linkage as the magnet is moving is rising for a particular coil, and then as it is completely aligned, it is going constant. So there is no further change in the flux linkage, and then it is falling down and once again having a constant value for some reason and then going so on. Same thing is observed with the other phases also. However, because the windings are arranged in a symmetrical fashion, which means that we are having 120-degree phase shift, between windings, the same phase shift is basically observed in the flux linkage also. This 120 degrees corresponding to the electrical angle. So based on the number of poles, we may find the mechanical angle also computed in that manner. Now, on account of this flux linkage, if we try to compute the back EMF, we need to effectively have the Faraday's law. Back EMF is nothing but the rate of change of the flux linkage, and so we are going to have a nearly trapezoidal structure for the back EMF. So what we can find here in this figure is basically the flux linkage which is varying in the fashion what we have seen, and then the EMF with respect to the corresponding flux linkage forms a trapezoidal structure in the coil. So which is why we say that this is non-sinusoidal structure, and to identify whether we are dealing with permanent magnet synchronous machine or brushless DC machine, this is one of the way to identify that. If we operate the motor mechanically without any electrical connection given to that, we are going to find the back EMF going in a trapezoidal fashion or nearly in that manner. So what our understanding is that as the EMF is changing in the motor and we are trying to supply power to the system, so we have the BLDC motor which is effectively connected to power converter. As I said, the commutation action has to happen through separate assembly, so the power converter helps in achieving the constant torque or uniform torque for the machine. So because of the supply provided to the unit, it is called DC machine, brushless DC, and because there are no brushes involved in this commutation process, so this is called brushless DC. Now what we find that if we are trying to inject or if we are trying to generate a uniform torque, it effectively means that we have to provide a uniform electrical power to the machine for operating the mechanical load assembly. So torque can be computed as the P electrical, nearly the power given to the machine divided by omega m. So we need to ensure that the power given to the machine is basically uniform, is unidirectional, and hence unidirectional torque can be achieved in this arrangement. So what we find here in this system is that, in this figure is that, the phase A is excited when the EMF is settled at a constant value which is corresponding to the steepest portion of the psi A, and the current is maintained constant over that duration. Further, when the EMF is again finding a negative constant value, the current is again maintained constant, however the direction of current is reversed to have a positive power. And this is repeated basically over the rest of the cycle. Similarly, what we are finding for the phase B is that as the EB is attaining a constant value, we are finding the constant current provided to the phase B. And then when EB goes negative, we have constant negative value provided for the phase B coil. The phase C also can be seen to have similar current provided in the system. So effectively what we are trying to have is that once again we are dealing with non-sinusoidal voltage and current, and we are trying to have pulsating current in the system. Now because BLDC can be more seen like a three-phase or multi-phase system, we can have inverter kind of arrangement for providing such currents. So one of the possibility could be is that we can have a three-phase inverter kind of arrangement, and as seen from the waveform, if we try to locate if one of the phases is having positive current, correspondingly there is this negative current flowing in the other phase. So we can always connect these two phases in series through the converter, and we can flow the current in such a manner that one of the coil is seeing positive current and the other coil is seeing negative current. So the switching of the devices can be coordinated in that manner. So for example, if we are trying to have positive current flowing through the A phase and negative current flowing through the C phase, we can turn on S1. So current flows in this fashion, and then S2 so that it can return back through the negative DC bus. Further, as the EMF is changing, what we are finding is that now the B phase has to come as positive and C phase has to come as negative. So S1 can be turned off and S3 can be turned on. So positive current can flow through B phase and negative current can come through the C phase. Later on, the negative current is basically shifting to A phase. So the bottom device for the R phase, which means S4, can be turned on. And the current can return through this path. So in this manner, by doing the operation of the devices in cyclic manner, we can maintain current flowing through the phases at a given value. So same can be observed over here as well. What we are finding that by having such operation, we are able to generate a uniform torque, almost uniform torque, and we can decide that in which mode we are operating the machine. So different combination of different switches can be called as different mode of operation, and the BLDC can be operated in this fashion. As suggested, the drive need to operate in a more controlled fashion. So we need to have, many a times we need to have the closed loop control. So typical closed loop control structure can be given like this for permanent magnet BLDC machine. So we have inverter which is basically feeding the machine, and we can have feedback of the currents. Now the most important part which we need to have for the BLDC and SRM machines is basically the encoder or Hall position sensor. So this basically provides the information about the theta at which the particular phase should be excited. So as the rotor is moving, this Hall effect based sensor can tell us the position of the rotor exactly, and with respect to that, which phase is going to have the current requirement, whether in the positive direction or negative direction, that can be identified. We may have speed computation on basis of the position, and then the reference for the speed can be taken with respect to the feedback through a PI controller, and then we can understand that how much current or torque requirement is there for the machine, and that same current reference can be provided to the respective reference current generator for the different phases. And then we can have the PWM regulator, as we have seen, for the hysteresis control. If we have to maintain the current at a certain value, it can be done in a fashion that the current is confined within a band and it is switched on and off based on the requirement. So in this manner, we can have a good regulation over the current value, and we can achieve the desired operation for the machine. So both the machines, SRM as well as BLDC, must have the Hall effect position sensor. However, there are certain techniques where the sensorless control of BLDC or SRM is also performed. So that is done on the basis of estimation of the flux on the SRM and estimation of the back EMF on the BLDC. So these are some of the things which we have found for the operation of SRM and BLDC. Now, if we take a quick recap of what all things we have done during the course, we have seen different types of systems for the electric vehicle in terms of what all type of motor drives are basically available for the industrial electric vehicle, and we have identified that it is dominated by permanent magnet, synchronous machine or induction machine, as we are targeting the high speed and high power applications. So we have understood very well how to operate the induction machine in open loop case, and from here we have seen the operation of inverter. We have also seen, because DC machine many a times gives the foundation for understanding the control, the closed loop control of the motor drive. So we have seen the closed loop control through DC chopper. Going on, we have further established the model of PMSM in rotor flux oriented frame of reference, and the same is extended for induction machine. In particular, we have seen the case of squirrel cage induction machine, and the vector control for both the systems, both the machines, is done over here. In the process, we have also seen different type of PWM schemes, including sine triangle, selective harmonic elimination, optimal pulse width modulation techniques, and how these techniques are basically impacting the current ripple and torque ripple, etc. Going ahead, we have also seen special machines which are basically forming a small segment in the electric vehicles for, say, low power applications, where we have the brushless DC motor based EVs or SRM based EVs, and we have seen that what is the fundamental behind the operation of these machines and how we can have the use of inverters or power converters for operating the system reliably. So with this, we close the course over here, and all the best to all the candidates. Thank you.